Welcome back. This is the second segment for section 3.2. And rather than a bunch of me babbling, let's go right to the problem that I had discussed last time, which was an idea of taking a certain amount of arc length and determining the radius of a wheel. I'm going to phrase that in a slightly different way. So let me just kind of pose this problem. So here's another example. Suppose you let's say you ride your bike for oh, I don't know, what sounds like a good distance. How about let's say 6.124 miles. This is a little bit more challenging problem, but there is a problem in the textbook that requests some additional conversions. And we'll say, and the radius of the wheel, let's say the wheels, let's suppose they're both the same size, is, let's say, what sounds like a good number? How about 18.3 inches? How many revolutions did the wheel make? Okay, so this is a little harder problem because almost everything in it has to be converted in one way or another. So understand first off that what the question is asking for, how many revolutions did the wheel make or the wheels make, is a question about angle. Okay, so we have the radius, we have the arc length. Now you have to make this connection that distance a wheel sort of moves when it's rotating is actually the arc length in some sense. Even though the center is kind of moving in space, which is kind of a weird idea and probably why this stuff's so challenging. But anyways, if we go back to our formula, S equal R theta, that's what this question is asking, is it's like find theta. So if we rearrange the equation to suit the variable that we're looking for, theta is equal to S over R, okay? Now remember, theta is going to be in radians. And in order for this to make sense, these have to be in the same units, and they clearly aren't. We have miles and inches. So in order to execute this and get theta into radians, we will need to convert either inches to miles or miles to inches. So I'm gonna opt for the latter. So this is equal to 6.124 miles. And then since I don't quickly know how many inches are in a mile, I'm going to convert this down to feet and then convert feet into inches. So I've got the unit I want to get to, 5280 feet, divided by the unit I want to get out of. Okay, now the miles in some sense will cancel out. We got one in the numerator, one in the denominator. Feet is what I'm left with now. One more step, 12 inches. So I've got the unit I want to get into divided by the unit I want to get out of. And then the total number of inches is 18.3. Now this, once I perform this calculation, this will give me the ratio of arc length to radius in a unitless number. Right? Inches on the top, inches on the bottom. That is the definition of a radian measure of an angle. So let's just maybe just calculate that out. Now notice, and we won't approximate it yet, but notice that this is there's 4 significant digits here, This is a conversion, so there's an infinite number of significant digits. Another conversion, infinite number of significant digits, a measured quantity with 3 significant digits. And so the net result of anything that we do during this calculation can at best be something with 3 significant digits. Okay, so let me just start over here. We'll take, kind of slide this up so we can still see it. The screen kind of wants to blank out there a little bit. So we have 6.124 times 5280. It's going to be divided by 1, which doesn't do anything, multiplied by 12. Again, divided by 1, which doesn't do anything, then divided by 18.3. And there's our number. It's kind of a little hard to see, but the decimal point is in the 5th digit between that 3 and that 0. So what is this telling us? Well, the answer that we've got so far is that this is 21203.0950 whatever. And remember, the units here are radians. Now, how do we get it into, notice that the question doesn't ask for radians, it asks for revolutions. So we'll need to convert this number to revolutions and then apply our significant digits. So I will just do it this way. That's this number. And I'll multiply it by so the units I'm in is radians. So I want to get into revolutions. My conversion is the thing I want to get into divided by the thing I want to get out of. So I'm basically just dividing this number by 2 pi. And it looks like I've got decimal place is between the 4 and the 5. Again, I apologize, it doesn't really show up real clearly. So this is approximately, well, I mean, 337.577 revs. I kind of ran out of space here. I'll maybe just squeeze it in right here at the end. But this is something that I've noticed repeatedly over the years, is that when a student is asked to round something off, if it's kind of close to the number, like if this had been 3, see, we'll round this to 3 significant digits. And when it's 337.1 or 3371 point something, that doesn't seem to be a problem. People don't have a problem rounding down to 7. And when maybe it's like 3369, again, people don't have a real problem rounding up. But for some reason, when the number's in the middle, right, where this is kind of close to the middle, it's almost as if people don't want to round that off. They're like, well, I don't know. I mean, that seems like a long distance to be rounding them off. But just stop that. Just stop that. The rules are pretty clear that you have to round to the number, a certain number of digits. So even though this is kind of close to the middle, it doesn't make any difference. It's either on the left side or the right side of the middle. And in this case, it's less than 3375, so it has to be rounded down. So our final answer here is going to be 3370 revolutions. Okay? And I mean, I'm not trying to get harsh on people. It's just I've seen people do that so many times, and I honestly don't understand why there's an apprehension about rounding numbers up and down when they happen to have, when that digit that needs to be rounded is like a 4 or 5, sometimes a 6. For whatever reason, people just want to add another significant digit, and it's like, that is absolutely wrong. That's not how it works. So let's move on to a different kind of problem that we have in this section, which is ones involving maybe sometimes wheels connected with like gears or pulleys or something like that. So let's suppose we have two gears that are in contact. Suppose the radius of the smaller gear is 3.6 inches, and the larger is 5.4 inches. If the smaller gear rotates by an angle of 150 degrees, how much does the larger gear rotate? I'm going to actually draw a little picture here. So here's kind of our smaller gear. Here's kind of our larger gear. And hopefully it's pretty clear that, I don't know, it's not a pair of eyes, but, you know, I'll put little gear bits on these things. These little sort of wedge shaped teeth that are on these gears, and that's what makes, if this one turns, then that one turns, and vice versa, because they don't slip or grind in there. So what the problem is saying is the smaller gear rotates, you know, a little over a quarter of the way, almost halfway. What does that do to the larger gear? And hopefully it's clear that the larger gear doesn't rotate as much. I mean, the number of teeth that pass through is the same. So that's what we're going to use to actually solve this problem. But that this one will actually rotate. If we were doing this like however, you know, in a certain amount of time, this one's maybe rotating pretty fast, and this one's rotating a little bit slower because of its larger size. So this maybe is something you haven't really thought about carefully about gears and whatnot, but there's a couple of different problems in this section that do talk about gears. And so I want to make this kind of clear, because a gear or pulley or whatever, as long as there's no slipping and sliding, the problems work exactly the same. So first off, notice that for each one of these circles, we can write this equation. So I'll just say, well, you know, S for the first gear equals the radius of the first gear times the angle that is subtended for the first gear. And similarly, for the second one, we have a similar equation. Now, the key to these kinds of problems is recognizing that how much ever, if you want to think, let's not even use the term arc length, but imagine as this wheel turns around, right, a certain number of teeth pass through, right, sort of the connection point. Well, the number of teeth that pass through on the other side has to be identical, right? So if say 16 teeth chunk through here, well, you'd have the same number of teeth that chunk through here, provided they're the same size. So this is really kind of a statement that the arc length will be the same. And that's in physics problems and other sorts of things like that, when you talk about rolling without slipping or sliding with, you know, any kind of rotation without slipping, this is exactly what's meant, is that the sort of surface distance on this roller or whatever it is identical to the one that's over here. So that kind of connection can be written this way: S1 equals S2, okay? And as a result, these right-hand sides of these equations are equal to each other as well. So we've got R1 theta 1 is equal to R2 theta 2. Now, at this point, remember, these equations are written in terms of, it only works when they're in radians. But it turns out for this equation, it really doesn't matter what unit any of this stuff is in, as long as it's in the same unit, right? So you have a distance, in this case, it's a radius that's in our problem, it's in inches. Radius in inches. Angle in degrees, this will give you an angle in degrees. So I'm gonna, for the problem in this case, I'm calling the smaller gear, gear 1, and the larger gear, gear 2. So what the question is asking for, how much does the larger gear rotate? That's a question about angle, and that's theta 2. So rearranging this equation, I have that the theta 2 is equal to theta 1 times the ratio R1 over R2. Okay? And we don't have to do any funny unit conversion because this is going to be a unitless number, provided that the radii are both measured in the same distance unit, which they are, and this is in degrees. So this answer will be in degrees. And we'll just go ahead and calculate it out. So theta 2 is equal to 150 degrees times the ratio, the smaller, 3.6, divided by the larger, 5.4. And notice everything on the right-hand side has 2 significant digits, so that's all we're going to get out of the problem. So let's start with 3.6 divided by 5.4. That's our ratio, 2/3. And then times 150 degrees gives us 100 degrees. So remember, this has 2 significant digits. And the way that we represent the digit of significance, if it's actually a 0, is to put a line over the top. So this tells us, at least, I mean, this is one way that I've seen it done, that this is two significant digits, not 3, not 1. So this is our final answer for this problem. Okay, so I've got a couple more examples that are kind of important. I mean, we could do more of this kind of stuff. I think we've already done, I've got another example of rotations, but involving some wheels and things. I think the previous example I have probably clears that up, and there's plenty in the book too, so feel free to look at those. But what I do want to do is there's a completely sort of tangential topic that's in this, this section, which is a discussion about what's called a sector. So section 2, on page 5. Okay, so I just want to, and the sectors really has to do with areas. So I want you to consider for a second kind of a circle and the radii. Consider this shape, right? This kind of ice cream cone shape. So this whole area is what's called a sector, or this shape, I guess. This shape is called a sector. Oops, sector. It is, sorry, it is a portion of a circle. And generally speaking, this angle down here, right? This thing will have a radius and it has an angle, and that's enough to determine anything we need to know about it. So theta in this context is usually called the central angle. Okay, so We use sectors, especially like highway design, civil engineering sort of things. There are some other applications, but usually when you're talking about a sector, you don't really care too much about, well, it's the relationship between the radius, the angle, and the area. So maybe I'll put up here a big capital A for the area of this sector. So there is a relationship between the central angle and the area. But I want you to kind of think about this, go back a second and recall what the area of a circle is. If you remember, the area of a circle is A equal pi r squared, okay? So now this is a complete circle. Now I want you to think about for a second, if you were to divide this circle in half, right? So you only have, you know, not a full revolution, but maybe just half a revolution, then this would be pi over 2 times r squared. And similarly, if you divide it into quarters or whatever else, you end up with making this smaller and smaller units. And that's sort of the way that this formula is developed, because this in some way is related to a full revolution, right? So if we were to insert theta into this equation and say, well, you know, what is it for, like, say, maybe 1 radian or whatever else? It turns out that this equation simplifies because this would be the situation where theta is 2 pi. So in some sense, we're wanting to put an equation where we've got A equal maybe a coefficient times r squared theta, where theta is in radians. I know this is a little kind of backwards to do this, but if theta was 2 pi radians, what would this coefficient need to be in order for this equation to hold for 2 pi? And it turns out that that answer is just 1/2. So just to verify, if we're talking about a whole circle, then the radian measure of the central angle is 2 pi. And the 2 will cancel with the 1/2 out front, and we're just left with pi. So the area of a circle is pi r squared. So that's a real dirty, quick derivation of this result, and it's kind of a little bit hand-wavy too. But it turns out that this is the equation for the area of a sector, provided that the central angle is measured in radians, and it hardly ever is. So let's look at a problem to kind of hammer this home. There's a few in the book. I think I asked you to do maybe 1 or 2. They're relatively easy. So again, most of these problems, the issue is going to be unit conversion, and remembering that you have to do all these problems in the right units. There's some times where you can kind of get away with it, like with that gear problem. But for the most part, that's the thing that you got to watch out for. It's not these formulas. I mean, we have 2 formulas: S equal r theta, and then area equal 1/2 r squared theta. Now, what I've noticed over the years is that students confuse these two, and they don't actually memorize the formulas. Then when it comes time to do it on a test, they're like, I don't know what I'm doing. So I would say memorize these formulas, because there's only 2 in the entire section, and they will come up on a test at some point. So and be able to work them, I guess. So let's suppose a lawn sprinkler has a range of, let's say, 25 feet, and is set to sweep out or sweep out an angle of, well, let's say 47 degrees. How much area will be watered. So let's be clear about what's being told here is that we have a distance. And if you think about the way sort of a sprinkler works, right? So in this one, 47 degrees. So we're sort of, here's our sprinkler, and it can water out to 25 feet. It's swinging through an angle of 47 degrees. And the question is, how much of the lawn is actually getting watered? Maybe not a real interesting problem, but so be it. So, but understand that the question is asking for how much area. And so we want to use an equation where we have A equals something. And of course, there it is. It's the most basic version. So we want A equal to 1/2 r squared theta. Remember, theta has to be in radians. So checking back to the parameters of the problem, it says that the range of the sprinkler is 25 feet. Well, it doesn't use the word radius, but this is what this is referring to, is that the radius of this shape is 25 feet. And then the angle, which is theta, is 47 degrees. Notice it's in the wrong units. So to calculate this, we have 1/2 25 feet squared times the angle times the conversion of that angle. Again, we need it in radians, and we want it out of degrees. And then we just calculate. So I've got 1/2 times 25 squared times 47 degrees. Then my conversion times pi divided by 180. And I've got 256.34 something or other. And the units on this are going to be square feet, because if you notice, here we end up with a unitless, radian unitless number, degrees divided by degrees, the degrees gone. But here we end up with feet squared, which is what areas should be in, right? Now, to apply significant digits, just like I said before, for some reason, people have a hard time rounding numbers like this off. Notice all of these measured quantities have 2 significant digits. This is not a measured quantity. This is a conversion factor, kind of like this. So when we round this, it has to round to this place where the 5 is. Even though this is a 6 and you're feeling like, oh my gosh, I can't round that much. Yes, you can. It's just follow the rules. This will round to 260 square feet. Okay. So don't, I mean, it sounds very childish. I'm not trying to treat you all like children, but the fact of the matter is I've seen people do this so many times that it's like, just get over yourself. You have to round to the correct place. That's the whole point of significant digits, even though I rail against them all the time. Okay, so I think that's probably enough examples for this section. There's a couple that you can, obviously in the homework, you can work on. And if you have any questions, this rotational stuff actually tends to be a little bit confusing. So it is not unusual that people have a lot of questions. So don't feel bad about asking something that seems really simple if you don't understand it, because it can be very challenging. Okay, so I will see you all in section 3.3.